So now we need to think about what happens when we have mixtures of gases. And here we need to apply Dalton's law. Dalton's law of partial pressures can be applied when we have a mixture of two or more gases. So let's start simple. Let's consider a mixture of only two gases. I'm going to call them A and B. We can write the total number of moles of the gas as N total. So N is the number of moles and N total is the total of number of moles of all gases. So the total here is going to be the number of moles of gas A plus the number of moles of gas B. All right, that's simple. Now, let's take this and substitute it into the ideal gas law. The ideal gas law is PV-NRT, PV equals nRT. So here we have PV equals nRT, where N is N total, the total number of moles of gas. So this is just expressing the ideal gas law for a mixture of gases where the total number of moles of gas is the number of moles. So remember that N total equals NA plus NB. So another way that we could write this is that PV equals NA plus NB times RT. Okay, so there I just substituted this expression in for N total. All right, so now I can distribute the RT through. If I distribute the RT through, it's apparent that PV is equal to N sub A times RT plus N sub B times RT. And I get that just by taking this RT and distributing it through the NA and NB terms here. So from there, if I divide both sides by the volume, I can see that I'm going to get a pressure for gas A that's going to be equal to the number of moles of gas A times R and T over the volume of the container. And similarly, I could write the same thing for the pressure of gas B, that the pressure of gas B is going to be equal to the number of moles of gas B times RT over the volume of the container. P total, the total pressure here, is going to be equal to the pressures exerted by both gases. So here, the pressure that comes from this term here and the pressure that comes from this term here divided by the volume is going to be equal to the total pressures. This brings us to Dalton's law of partial pressures. So you can kind of see where this is coming from. Dalton's law states that the total pressure of a gas mixture, so a mixture is when we have two or more gases together, is going to be equal to the sum of the partial pressures that are exerted by each gas. So in that example, I just did only two gases, but this could go up to however many gases you have. Gas A, pressure of gas A, plus the pressure of gas B, plus the pressure of gas D, etc., etc., etc. So each individual gas in the mixture is going to exert its own pressure. And if I add all of those pressures up, I get the total pressure of the gas mixture. It's very simple. That's all that Dalton's law tells us. So let's do some examples. A volume of 2 liters of helium gas at 46 degrees Celsius and 1.2 atmospheres of pressure is added to a container of 4.5 liters of nitrogen gas, which is at STP. Remember, STP is standard temperature and pressure. What is the total pressure of the mixture of two gases once we add them together? And what are the partial pressures of each gas at 273 Kelvin after the helium is added? So we need to figure out the total pressure, and we need to figure out the partial pressures of each gas. And it looks like for nitrogen, we have a fixed volume for our container, 4.5 liters. So we have nitrogen in that container, and we're going to be injecting helium into that container. So the total volume is not going to change. That container is going to be constrained at 4.5 liters. of the final mixture. But for the helium, we have a volume of 2 liters at 46 degrees Celsius and 1.2 atmospheres. So I can use that initial bit of information to figure out the number of moles of helium that I'm adding. So I think that's a good strategy. We need to figure out or calculate the number of moles of helium that we are injecting into nitrogen's container. So I can do that using the information that was given about the helium. So remember, the ideal gas law is PV equals nRT. And if I want to figure out the number of moles of helium, I'm just going to put the N sub HE. Now, for the helium gas, they told me initially I had the pressure of 1.2 atmospheres. I had a temperature of 46 degrees Celsius. But remember that you need to convert that to Kelvin. So make sure that you convert the temperatures to Kelvin whenever you're doing these ideal gas law equations. So carry the 1. This is going to be 319 Kelvin. The volume of helium's container initially was 2 liters. And again, I'm just using that initial set of data to figure out the number of moles of helium. R is the gas constant, okay, so that you can look up. It's 0.08206 liter atmospheres per mole Kelvin. All right, so I can rearrange the ideal gas law now to solve for the number of moles of helium. The number of moles of helium is going to be PV, oops, did not write that correctly, PV over RT. So that's going to be 1.2 atmospheres times 2 liters divided by the gas constant, 0.08206 liter atmospheres per mole Kelvin. And that is going to be multiplied by the Kelvin temperature, which is 319. So make sure your units are matching and that you can cancel the undesired ones. So moles is in the denominator of the denominator, so it flips to the top. And if you do that arithmetic in your calculator, you should get 0.0917 moles of helium. So that calculation was important because it told me how many moles of helium I am injecting into the container. So remember that I'm adding that many moles of helium to a container that contains 4.5 liters of nitrogen gas, which is at standard temperature and pressure. Standard temperature and pressure is defined as 0 degrees Celsius, which of course is 273 Kelvin, and 1 atmosphere. So that means that when I do the calculation for nitrogen, I have the pressure and the temperature defined by that STP. So I want to figure out the total pressure and then the partial pressures of each gas, which I guess is still going to be at 0 degrees Celsius or 273 Kelvin after the helium is injected into nitrogen's container. So let's think about the total pressure first. The total pressure is going to be equal, by Dalton's law, to the sum of the pressures of each individual gas. Okay, this is Dalton's law for this problem. The pressure exerted by the helium plus the pressure exerted by the nitrogen is going to be equal to the total pressure of the mixture. So we know the pressure of the nitrogen gas because they told us that the nitrogen gas is at STP, and STP has a defined pressure of 1 atmosphere. So the pressure of nitrogen is going to be 1 atmosphere because it was at STP. Now, we knew the pressure of helium before it was added, but this doesn't apply to the new container. So we need to think about the new container and what the pressure of helium is going to be in that new container. In the new container, the pressure of helium is going to be given by the number of moles of helium times RT over the volume of that new container. Now, I know the number of moles of helium because I calculated it. So I'm going to insert that into this expression, 0.0917 moles of helium times the gas constant, 0.08206 liter atmospheres per mole Kelvin, times the Kelvin temperature in the new container. Now, they told me that the new container is going to be at 273 Kelvin. So that is the value that you want to put in here, 273 Kelvin. This applies to the new container. The volume of the new container is 4.5 liters. So doing all of that gives me a pressure of helium of 0.46 atmospheres. Now, what these are actually partial pressures, right? Because nitrogen and helium are a mixture of gases. The nitrogen exerts a pressure of 1 atmosphere, and the helium exerts a partial pressure of 0.46 atmospheres. So the total pressure is equal to the partial pressures of each gas. It's partial pressure of nitrogen plus the partial pressure of helium, and that's 1 atmosphere plus 0.46 atmospheres. So the total pressure is going to be 1.46 atmospheres. This is going to be the total pressure of the gas mixture. The other question was, what are the partial pressures of each gas after the helium is added? So adding the helium doesn't change the pressure of the nitrogen. So the partial pressure of nitrogen is going to be 1 atmosphere. And of course, the partial pressure of helium is what we just calculated. The partial pressure of helium is going to be 0.46 atmospheres. So these are the 3 answers that I need to address this question.